Hi there, students. Mrs. Brunk here again. And today we're going to wrap up our solving quadratic equations methods with the quadratic formula. So we've been talking about all the different ways, and we've even kind of looked at the best times to use different ones. And we learned the graphing, which is really not a legitimate way to solve quadratics because first of all, it's kind of cumbersome to have to graph. A lot of the solutions are not going to be nice integer values. So we looked at that just to kind of get an idea of what we meant when we said solutions. We mean where the graph crosses the x-axis, so the x-intercepts. And then we went on and learned how to use factoring to solve with the zero product property. We talked about the square roots method. That was especially helpful when there was no bx term. And then we finally learned the completing the square method, which was something we could use when our quadratic wasn't factorable. We couldn't use one of the other methods. And we kept mentioning that there's one method that really could be used to solve any quadratic, which is similar to completing the square, although completing the square can be very difficult in certain circumstances. But the quadratic formula was the final one, and it can be used to solve all quadratics. So why do we not just learn that one? Because it works for all of them. Because it's not always the easiest, and I think we're going to see that today. We're actually going to begin by looking at a part of the quadratic formula. It's called the discriminant. Now we'll reveal the whole quadratic formula here eventually, but there's going to be a part in it that's called the discriminant, and it looks like this. B squared minus 4ac. And so when we are talking about a, b, and c, we mean standard form equations. So that's ax squared plus bx plus c. So in other words, when we have something that's in standard form, with 0 on the other side, the b squared minus 4ac is the b, which is the coefficient of the x, squared minus 4 times the a, which is the coefficient of the x squared, times the c. And we're going to find out that that is actually part of the quadratic formula, and this discriminant on its own tells us a lot of information about the kinds of solutions and the number of solutions that we will get for the quadratic, which means it will also help us maybe to decide what method would be best to solve. So let's take a look at the 3 or 4, I guess it's technically 3 different possibilities, but we kind of take one of them and break it down a little bit more. But what about if we calculate b squared minus 4ac and we get a number that's greater than 0? So that's the scenario that you see here. The discriminant, is greater than 0. So in other words, if you get a positive number, okay? Now, there's 2 things that could happen. If you got a positive number and it's a perfect square, then that means you're going to end up getting 2 real solutions, 2 real roots for the equation. So you can kind of imagine what that looks like. It means that you're going to have a quadratic parabola that is going to cross the x-axis in 2 distinct spots, right? But the type of roots that we're going to get are going to be rational. So we'll see that in a second. And by rational, we mean that it doesn't have any radical parts to it. So it doesn't have any square roots. It comes out to be just a rational number. Okay. Now, if we got a positive discriminant, but it's not a perfect square, then that still means that the graph's going to cross the x-axis twice. There's still going to be 2 roots. But we're going to end up with irrational solutions. And what that means is if we leave them the exact form, we will have some sort of radical as part of our answer. And if we were to approximate them, we would get some decimal that we would have to round. Now, sometimes you'll find the discriminant and you get exactly 0. And if you do, that actually means that you'll get exactly 1 solution. This is the kind of parabola that just sits right on the x-axis. It would look like, let's see if I can draw that a little better. It would look like this. It's going to have its vertex sitting right on the x-axis. Okay? And then the ones where the discriminant was positive, you're going to have it crossed twice like this. Okay? So if you get one solution, so it would actually be rational. And both of these terms, rational and irrational, they refer to numbers that are real. Okay, they're real numbers. So also I should include that it's real numbers. And that means, graphically, it means it crosses the x-axis, the real axis. Now, if we got a discriminant that is a negative number, and I think you'll see this as soon as we see the whole quadratic formula, but if we get a negative number, it actually means that there are actually still two solutions or roots, but they are non-real or imaginary, so we've called them that too. And that actually means graphically, it means that the graph doesn't really cross the x-axis, it crosses some imaginary axis. So that's because we end up taking a square root of a negative number. You'll see that the discriminant lies under a square root. So if you get a negative discriminant, you'll have to take the square root of a negative number, and that means you're going to get, as part of your answer, an I, so an imaginary part, so meaning that it would be a non-real solution. So we're going to first just practice finding the discriminant, and then we're going to introduce the whole quadratic formula. So first of all, you always want to make sure your equation's in standard form. So it has to be in that everything on the same side, 0 on the other, in descending order powers and all that. So then you can identify the A. So this is the A. That's A, right? This is the B. And then the C is actually a negative 11, right? Or not negative 11, negative 13, excuse me. So you always want to make sure it's also written as addition. So, so the B squared, so that would be saying take 12. Always encourage parentheses just in case it's a negative you're squaring. So B squared minus 4 times the A times the C. And when I calculate that, I get 248. Put that in my calculator, I got 248. And what that means is I have 248. So 248 is not a perfect square, but it is positive. So it's that second situation where I have two irrational real roots. So they are real. There's two of them, and they're irrational. Oops. Okay, how about number 2? So again, we've got the A, B, and the C. The B is 16, so that would be 16 squared minus 4 times the A. The A is negative 1, and the C, which is negative 64. So I've got 256, which is 16 squared. And then I have minus 4 times minus 1 times minus 64. That's going to be a negative. And that's going to be a negative 256 as well. So this turns out to be 0. And what that means is I've got one real, and it's going to be rational. In other words, it's not going to have a radical in my solution. It's going to be one of those quadratics that sits right on the x-axis. So one real rational. So we'll put this all together when we actually use the quadratic formula, but for now we're just using it to kind of diagnose. Number 3. So number 3, and then we'll actually do put it in standard form, and then I'll have you calculate as a you try question. So let's first put everything on the same side. Typically when I do this, and I can rearrange my quadratic, I usually try to make it so that the leading term, so that the x squared term is positive. Here I could go either way, and I'm still going to get the same discriminant. So I think I'm going to bring these two things over to this side, just to make sure that the x squared term is positive. Just makes it a little easier for me. So that actually would make it 4x squared minus, plus 10x minus 84. So again, when these come over to the other side, they're going to change sign. So flip them over to the other side. The 4x squared becomes positive and the 84 becomes negative. So now my b squared would be 10 squared. Oops, I was going to let you guys do that one as you try. So I guess you can pause the video now if you want and give that one a try. Otherwise, just stay with me and I'll show the solution here. Okay, so b is 10, so that's 10 squared minus 4 times the a, which is 4, times the c, which is negative 84. Now that turns out to equal 1,444. And that is actually a perfect square. It's not one that's really commonly known, but I always check to see, so I took the square root of it, and I got 38. So I know that that's a perfect square. And so that actually means that I'm going to have two real, and they're going to be rational roots. So I shouldn't expect to have radicals for that because it's a positive real number that is a perfect square. So now the next one, notice this one does not have a b. So that means the b is 0. So this would be 0 squared minus 4 times the a, which is 3, times the c, which is 24. And certainly that's going to be something negative. So that's negative 4 times 3 times 24, which is negative 288. And because I have a negative number, I know that that's going to be two non-real solutions or imaginary solutions. Okay, so here it is, the quadratic formula. Now I know that this is something that you are introduced to and use even a little bit in Algebra 1. So hopefully it'll be familiar. You may even know a song that might help you remember this. If you don't, I will certainly share with you a lot of them that I know. And I'm going to post up on the Google Classroom or website or whatever with some of my favorites, and I'll share with you in class some of my favorites. But the one that I always remember, I still come back to, even though I hear some that I like a lot better, was one that I learned that comes from a college fight song. And this is the one that I always remembered. Because when you want to use the quadratic formula, you don't want to have to look it up all the time, right? So this is how I remembered the quadratic formula. Pardon the singing. X equals opposite of b plus or minus square root b squared minus 4ac all over 2a. Solve, solve, solve. Oh my gosh, I'm so sorry about that. That was terrible. Well, I'm certain that you'll find some that are a little more pleasing to your ears, but it still does the purpose, which it helps you to remember the quadratic formula. So however you learn it, that's completely up to you. But that's just was the first way that someone taught me. So, and you may have noticed the b squared minus 4ac. You see that discriminant we just talked about, right? And so that's actually part of the quadratic formula, and of course it's under a square root. And that's why it mattered whether we got a positive number, whether we got 0, or we got a negative number, and it predicted the number of solutions and the kind they'd be. Because when you take the square root of a positive number, you always get two possibilities, a positive and a negative version, right? When you take the square root of 0, there's just one square root to 0. And when you square root a negative number, that means you're always going to get something that involves I, which means it's imaginary. So let's take a look at trying to use the quadratic formula in its entirety, not just to see what kind of solutions, but to actually get solutions. Okay? And we may see that maybe it's not always the best one to use. Sometimes it's the only one we can use. So in this first one, number 1, so if I wanted to use the quadratic formula, I'd just say x, the solutions, equals the opposite of b. Well, b is 2, so the opposite of that is negative 2. Plus or minus, so that plus or minus there that's in that formula is the fact that when you square root, you're going to, unless it's 0, you're going to get a positive and a negative root, right? B squared, so the b squared would be 2 squared minus 4 times a, which is 1, times the c, which is negative 63, and then all over 2 times a. Well, a is 1, so 2 times 1 is 2. So now we got to simplify this. So that's negative 2 plus or minus. Now we've got to figure out what the discriminant is. So 2 squared minus 4 times 1 times negative 63 turns out to be 256 all over 2. Well, just looking at the discriminant, that 256, remember that's a perfect square. So when that's a perfect square like that, that means we're going to get rational solutions. We're not even going to have a radical left in our answer. And that's because if we go ahead and take that square root, so we have negative 2 plus or minus, well, the square root of 256 is 16, right? It's positive and negative 16 all over 2. And so what that really means is my two solutions are negative 2 plus 16 divided by 2 and negative 2 minus 16 divided by 2. And negative 2 plus 16 is 14 divided by 2 is 7. And negative 2 minus 16 is negative 18 divided by 2, which is negative 9. So our solutions are actually 7 and negative 9. Now, these solutions came out really nice, 7 and negative 9. And if you recall, when we solve by factoring, we always either get really nice integer values or we get really simple fractions, like maybe 1/5 and 3/4 or negative, stuff like that. Like all the ones we've done when we had to do the AC method, we might have gotten a fraction, but it was a nice simple fraction, which would be a rational number. And in fact, any time the discriminant is a perfect square like this, then we would have probably been better off using factoring because you see how this work, right? But if instead I had just thought about checking to see if this was factorable, I'm just going to take all this off and show you we could factor this instead. Okay, is we could have just done the factoring, and we have two factors that will start with x and end with numbers that multiply to negative 63 and add to positive 2, which would be a positive 9 and a negative 7, and there's our solution, x equals negative 9 and x equals 7. So in effect, just being able to do that discriminant ahead of time and seeing that, oh hey, that's going to be a nice number, it could have led us to picking an easier method. So number 2, again, let's try the quadratic formula. This may not be the best method, and we might find that out, but just as we're starting to kind of learn the quadratic formula, just, it gives us some extra practice. So let's see. X equals the opposite of b. So b is negative 11, so the opposite of that would be 11 plus or minus the square root of negative 11 squared. So I like to do some of this just in pieces. So I know that negative 11 squared is 121 minus 4 times a. So 4 times a would be 4 times 6, that's 24, times negative 10 is negative 240. So that's going to be minus a negative, which is going to make that a plus. And then all over 2 times a. Well, 2 times 6 is 12. So again, I'm just I find that just strictly substituting those values in can get a little bit overwhelming with all the calculations. So I just do little bits at a time, and I tend to make less mistakes. So that would be 11 plus or minus the square root of. Well, when I add those together, I get positive 361, because it's minus negative, which turns that into plus positive, right? So 121 and 240 is 361, and then divided by 12. Well, 361, you may recognize, is one of those perfect squares. It actually is the, oops, hold on just a second. It is 19 squared. So this really means that's 11 plus or minus 19 over 12. And that means there's 11 plus 19 divided by 12, and 11 minus 19 divided by 12. And to simplify those, let's see, 11 plus 19 is 20. 20 twelfths would reduce down to, they both have a common factor of, let's see, 4 goes into both, so that would be 5/3. And then 11 minus 19 would be negative 8, so then I have negative 8 twelfths, which would reduce to negative 2/3. So I see solutions like that when I use the AC method. So if we actually went back and looked at this, the A and the C, that's negative 60. Are there factors of negative 60 to add to negative 11? Yep, negative 15 and 4. So we could have factored this and used the AC method instead. And just seeing that discriminant, that b squared minus 4ac part was 361, which is a perfect square, that just meant, yeah, I could do factoring. So was this one much harder than doing the AC factoring? Maybe not. So when it's a really easy one, like number 1, I would always try to factor it if I can. Might as well give it a shot. And if, I would say with 2, it's kind of a toss-up. It took probably about as much time to do the quadratic formula as it would have taken us to do the AC method. The only problem is with the quadratic formula, there's lots of opportunities to make mistakes. All right, so let's try a few more. So number 3, first thing is I got to get it in standard form, because you need to have it in standard form anyway to use the quadratic formula. So when I bring that 4x over and the minus 9 is still there. Now I just bring the 4x over, makes it negative 4x, and say I want to use the quadratic formula. But I might even have thought twice about completing the square here, because this actually one would be a pretty easy one to complete the square because it starts with 1, right? And it's got an even middle term. So again, our goal here is to try to practice the quadratic formula, but when it comes down to like later on trying to pick a method, this might be, using completing the square. And maybe I'll show both ways on this one. So x equals opposite of b, so it's opposite of negative 4, which is 4, plus or minus the square root of b squared. So negative 4 squared is positive 16, minus 4 times 1 times negative 9. So 4 times 1 is 4, times negative 9 is negative 36, so that's minus negative 36. All over 2a, so 2 times 1 is 2. So let's see, 16 and 36, because that's plus a positive, right? Minus negative makes plus positive, would make 52. So simplifying this would give us 4 plus or minus the square root of 52 over 2. And the biggest perfect square that's in 52, I believe, is 4. We could rewrite this as the square root of 4 and the square root of 13, which would make that 2 square root of 13. So that top simplifies to 4 plus or minus 2 square root of 13 over 2. Now in a situation like this, we can actually simplify this because both of the numbers on the numerator that are outside of radicals are both divisible by 2. So I could just take, and each thing I could divide by 2. And that would simplify down to 2 plus or minus, so the 2's cancel in front of the square root of 3, or 13, so then the 2 plus or minus the square root of 13. And actually, if we did completing the square method, that's what we would have gotten. And we wouldn't have to worry about reducing, and we wouldn't really have to worry about these issues that might arise, like, when you're subtracting 4ac if you get the sign wrong. So, it's not a bad idea to, qualify your question at the beginning, like just kind of go through all the choices. And I always think of quadratic formula as sort of my last resort. So that's my tool I go to last. All right, let's try another one. So number 4. So number 4, we've got 2 terms on one side and 2 terms on the other. Now when I get a choice, I always want to try to make sure my leading coefficient, that means my a, is positive. So for me, I'm going to move these 2 things over to the other side, and that will change their sign. So I'll have 0 left over here. I'll have 2x squared. I have the plus 8x, it's already over there. I am subtracting 17, and then so it's a minus 1 minus 17 is minus 18. And right away, I kind of see again, like, I know the goal here is to use the quadratic formula, but I see right here that, and I might still use it, but I see that everything is divisible by 2 here. So one thing I could do to, even if it isn't factorable, to make things a little easier is divide that 2 off. So I'm always looking for ways to make a simpler equation no matter what method I'm using. So that would actually make 0 equals x squared plus 4x minus 9. And now I know I still cannot use factoring here because I immediately checked factors of -9 that add to 4. Nope, there's not. But now I have smaller numbers to work with, whether I use quadratic formula or maybe I'll use the complete the square method. And actually, I think that's what I'm going to do here. I'm going to do the completing the square. So swing the 9 back over to the other side. Okay. I'll end up adding something here. Figure out what I'm going to add to make this a perfect square, which would be half of 4 squared. So that would be 2 squared, which is 4. So I'm going to add 4 to both sides. That makes this side 13. And this side, when I write it as a perfect square, is x plus 2 squared. And all I have to do is take the square root of both sides. And I end up with x plus 2 equals plus or minus the square root of 13, right? And then I'll subtract 2. So that's -2 plus or minus the square root of 13. And that's my final answer. Now I would have gotten the same thing had I used the quadratic formula, but I would have gotten into a situation like the prior question where I may have had to reduce. So this is just kind of, I get simpler numbers, I can avoid that. Also, if I hadn't seen dividing that 2 off, I would have had more complicated numbers, and they may have had a radical that I would have been able to pull a perfect square out of. But by just doing little things like looking for something that you can divide out of all the terms, or seeing if maybe completing the square might make things a little bit simpler, will just make your job solving quadratics much easier. Okay, so how about number 5? So this time on number 5, I put this in standard form, but what I noticed right away is that there is no x term. So rather than do that, I'm not even going to bother putting this in standard form because when there's no x term, I know I always use the square roots property to solve this. And so rather than go through all of that and end up having to use the quadratic formula, which then, every place where there's a b in the quadratic formula, I'd have to put a 0 in. And that might even get complicated, just, putting zeros in instead of actual, other coefficients. So I'm just going to use the square roots method here. So I'm just starting to kind of, distinguish which ones work best. So if I subtract 7 from both sides, that's 4 minus 7, so that's -3. And then I'm going to divide both sides by -8, which gives me x squared equals 3/8. And now I got to take the square root of both sides. Okay, so now this is a little bit tricky because when you square root you can't really square root the top. So that's the square root of 3 on the top. But on the bottom, I can pull out a perfect square. So I could rewrite this on bottom as the square root of 4 times the square root of 2, which is 2 square root of 2. But the problem there is I have a radical on the bottom, and hopefully you remember from back in Algebra 1, we're not supposed to have radicals on the denominator. Just like we talked about, you can't have imaginary numbers on the denominator. So what we're going to have to do is multiply the top and the bottom by a square root of 2 to get rid of that radical. And that's going to change my answer to, let's see, that's the square root of 6 on the top, and on the bottom that's the 2 times the square root of 2 times the square root of 2, which the square root of 2 times the square root of 2 is the square root of 4, which is 2, and 2 times 2 is 4. So that gives us the square root of 6 over 4, and that's plus or minus. And those are our 2 solutions. All right, so let's try one more, and then we'll have a couple U tries. So number 6, when we put it in standard form, would look like this: -x squared plus 10x minus 8 or we could have taken the negative x squared and the positive 10x to the other side. So we could either do that, use this one, or we could again put the negative x squared to the other side would make it x squared, the 10x to the other side would make it negative 10x, and then of course the 8 was positive. So either way, I personally like it this way because remember the denominator of the quadratic formula is 2 times a. And so if the leading coefficient, if the a was negative, that's going to make that denominator of that fraction negative. And I'm just never comfortable having a negative on a denominator of a fraction. So so I usually like to do it like this. I'll put everything on the side that makes the leading term positive. So putting it in this form, right away, like I kind of, at first I was thinking quadratic formula, but now when I look at this, looks like a really easy one to do with completing the square. So I think that's what I'm going to try. I'm going to try the completing the square method. And so to do that, I'm just going to swing that 8 back to the other side. And then I'm going to figure out what do I have to add to make that a perfect square. So whatever I add, I'm going to add to the other side. And so half of the middle term, which is negative 5 squared, is 25. And then I'm just going to add 25 on the other side, which is going to make my perfect square on this side, x minus 5 squared. On the right-hand side, I have negative 8 plus 25, which makes 17. And then I just simply have to take the square root of both sides. There's nothing I can do to simplify that 17, so that's a plus or minus the square root of 17. So let's see, x minus 5 equals plus or minus the square root of 17. So that means my final answer, if I bring that 5 to the other side, will be positive 5 plus or minus the square root of 17. Now, I would really encourage you, if you're kind of questioning why you would ever use the completing the square method rather than the quadratic formula, I think sometimes people get enticed by the fact that the quadratic formula works for everything. Give this one a try with the quadratic formula. What you're going to find out is there's a lot more steps to get to this nice simplified answer of 5 plus or minus the square root of 17 than we had to do with completing the square. This situation is like the ideal place to use completing the square. Our quadratic starts off with x squared and our middle term is an even number. That is the ideal time to use completing the square. So rather than do 7 and 8 as you try questions at this point, I'd like to move to our last page of our notes, and that's where we kind of try to put all this together and start to kind of train you how to think about the equations that you have to solve and to decide which method you want to use. So this step 1 says to find the discriminant of each equation and give the number and type of roots. So remember that discriminant, when we find that, should give us an idea of whether we can use factoring, which would of course be the easiest method, or maybe if we would want to use the completing the square method, or maybe we could do the square roots property if it's doesn't have a middle term. And then finally, if we can't use any of those, we go to our plan D, which would be the quadratic formula. So let's see, the discriminant, the b squared minus 4ac, so let's see, that's negative 9. Oops, negative 9. Squared minus 4 times 1 times 21. So that's 81 minus 84, which is a negative number. That's negative 3. So that means that I'm going to have one of those non-real solutions. So that means I'm either going to use the completing the square method. If this had an even middle term, I would consider that, but it's got a 9 there, negative 9. So I'm definitely going to use quadratic formula on this one. So that's what I'm going to do here. I'm going to put this one, I'm going to do A with the quadratic formula. B is that perfect one for doing the square roots property. Notice there's not a B term, so when we do the b squared, it's actually 0 squared minus 4 times the A, which is negative 2, times the C, which is 144, and regardless of what that turns out to be, I know it's going to be a positive number because it's negative 4 times negative 2 times 144. So that's definitely going to be a positive number. And that turns out to be 1,152. And that is not a perfect square. And so I know that my solutions are going to be irrational, which means this is not going to be factorable. So this is going to be one I'm going to use square roots for anyway. So no really need to worry about that. Equation C. So let's see. So the discriminant is b squared. So that's negative 22 squared is, that's 486. So that's the negative 22 squared is 480. Oops, I'm sorry, I meant to say 484. And then the 4AC part is 84. And so 484 minus 84 is 400, and that's a perfect square. So I know that this is going to have rational and real roots, and there's going to be 2, okay, because it's a perfect square. That first one would be non-real, okay, so which means I can't factor that. The second one is going to be irrational because that's not a perfect square, but real. And of course there's 2 again because that's positive. So 2, irrational, real. And then finally this last one, so that's equation C then, because it's rational and real. Then we could use the factoring method. We should be able to factor that. And finally, equation D. So equation D, that's the b squared, so that's 36 minus 4 times 1 times negative 15. And that's 36, let's see, that makes 96. So 96 is another one that's going to give you 2 real, but irrational ones, because that's not a perfect square. So I know I'm going to have some kind of square root in my final answer. So, but that one is a perfect one for doing complete the square, because see, the middle term is positive. Oops, sorry, not positive, is even, and it starts with a 1. So that's a perfect one for complete the square. So we have one that really is best suited for each type. So with that being said, this is a good place for some you-try questions. So I want you to give the indicated equation a try, given the specific method that's listed. So I want you to pause the video now, try factoring for C, try square roots for B, try completing the square for D, and try the quadratic formula for your first one on your own for equation A. So pause the video now and give these all a try. All right, so go ahead and take a look at your answers and compare them to the answers listed here. And if you have any questions, be sure to bring them up when I see you in class. But this actually kind of brings us full circle. All of the methods that we've learned, and really just looking at how to pick the best tool for the particular job that we have to do. I guess I'll see you in class.